lucky guess. Properly, you go through all the steps, you figure out which way it's going to accelerate. That way, we'll tell you which way the friction is going to act. Once you know which way the friction is going to act, you then solve it for use of S. It turns out it's moving, so you then plug in use of K. I hated those problems as a student. So that's why. So if you get one like that, I would break it down for you. This one, I would first, what is the acceleration? So at least you've demonstrated something. Sorry, if it were frictionless, what would be the acceleration? And then I throw friction into it as sort of part of the.
Okay, so that's why you do the multiple parts, just to help us keep track of how we're supposed to go along with the problem. Because I used to get a lot of that in chemistry too. In like general chemistry too, it'd be a problem. It'd be like, here are the numbers, here's what I need. But I'd have no idea how to get there. You just gotta keep track. And then next thing you know, you got a page worth of what maybe the answer is. No idea if you're good or not.
Probably one of my favorite 251 tests, there are a couple of them, but the Rube Goldberg test, where in theory, if I looked at the last answer and saw that it was correct,
Yeah.
then I knew everything else was correct. Well, all but one part.
Yeah.
Wow.
That's a scary test.
Yeah, no, that'd be horrible. Just get the whole thing wrong because I messed up the first step.
What I did also was I gave a number, and after the problem I said, if you cannot solve this, use this number to solve the rest of it. It did not go over well in general, but I still like the test.
So you pretty much said if you can't figure out the answer to continue with the problem, here it is.
Yeah, just not here's the answer, here's a number, and all the numbers were in the ballpark.
Okay.
You know, those like
Yeah.
within a factor of 2 of the right answer.
So you changed them just enough so you knew that they didn't get the other part.
Correct.
Okay.
And I had a spreadsheet set up so that, oh, they used 10 here, okay, so we pop a 10 in, so here's what all the rest of their answers should look like. So incredibly easy to grade. But again, it did not go over well with the students when we had to actually take it.
Well, that's fine, but that's kind of genius. You had a spreadsheet up, you put in the answer, and it tells you the rest. Like,
Yep.
that's,
Yeah, it was nice.
yeah. I would go with that.
Don't encourage. No, I don't think. Yeah.
All right, so anyway, let's take a break here, stretch legs. And we will come back and do more exciting some of this stuff or talk about energy.
Because I looked up an equation for that.
Oh, that's
Yeah, that, I think every semester I see that and think, I need to take that out because it's too soon. Kinetic energy shows up later. And somehow it keeps showing up again and again because I forget.
Bless you.
You can skip the kinetic energy or
Bless you.
kinetic energy as talked about on the Zoom call last night.
1/2 mv squared.
That's right.
Okay, yeah.
I remember that.
Yeah. Perfect. That's what I
All of
plugged
you should
in.
remember. So it'll be the same as whatever the speed is. Because I think all the masses are the same. It was same mass in different orbits.
No, the masses are different actually.
Okay. Then there could be some adjustment there. But anyway, the formula, as Britton said, or all of you said in unison and it sounded like a single voice.
Yeah. Oh, I have a question on the AU units. I mean, I gave you a jumbled mess of units, and I was like,
That's the simple way.
oh, really?
Yeah, if because there's so many things that it's one in some particular unit system. So if you come up with a jumbled set of units, potentially you have a numeric answer of 1. Or
So-
some ratio of pi.
As long as it makes sense, he wouldn't get points off for that.
Right.
I was gonna ask about that, like
Okay.
if
Yeah,
the units aren't in kilograms for that, because I'm assuming he's asking
Like that-
Yes,
one
yeah,
second
That
mass
one
of
time that
sun.
we had, like, in the bottom, seconds to the -1 to the -1/2 squared or whatever.
Right.
An
That
issue.
would have been fine if that was what, if after all of it, the units were right.
Yeah. So
I divide.
Unless I specify SI units, then, or even though seconds to the negative 1/2 or whatever it is,
Yeah.
that's still SI units, but.
No, yeah. I don't know if when that question came up, I was having a hard time figuring out how the unit should go. I had like the exponents and everything lined up, but I didn't know what my final answer was
Wait,
supposed to be.
what question?
It was one where
You have to figure out the mass of
I
the sun.
still had kilograms,
Unlike the master.
but it was I took
One
the
of the-
kilograms
one of
from
the other
the
older master sets.
like
from the units of the
from
gravitational
semester
constant.
class, like a current one.
Oh, okay.
Okay.
Is that okay? It's kilograms squared or divided by kilo. It's a mess.
Um,
No, that's what.
But I just took
that's what I'm
each
saying.
individual
Like,
unit
it's
and
probably
See,
I
at
always-
this point, I was on now.
What, G?
Oh, so I don't take G. There's no G.
Well,
We had to do this twice.
No G.
One
Three
G.
hours. Like
So
3 hours of
in place
class.
of G, instead of
I
putting
can
in
deal
the
with the 3-hour class once a week.
6.67 times 10 to the negative 11.
But I zoned out by like hour two.
Yeah, at like right
Yeah.
now.
That's what I'm saying. But
That's why I kind of like the one.
then what? I don't mind that online.
Just because it's like an hour and 20 minutes.
I've spent already.
I'll be making breakfast. and some other shit.
Yeah.
Can I still get credit for what I did here, or no?
Yeah.
I have to change
I
that.
get
too.
No,
I'm pretty
No,
I
halfway
think
through
it's
my
work,
days.
But I
done.
calculated this
30
with
pretty
G
much.
is
No,
like
I work in
6.67
the
times 10
afternoons.
to the
So I'll get home at like 11, and I'll sit down and do it.
let's see the derivation.
By the time I'm in bed,
Yeah, I
it's
mean-
already 2, 3 in the morning.
I tried to set it up so that you didn't have to do. You didn't have to
Yeah,
get
I'm in the bed
However,
by like 10.
There are multiple answers that are
I'm an
acceptable.
old man.
It'll
If
take
you-
me
gotta
10
go
minutes
early
if you
for work,
want it
so-
like this.
I still am.
So,
It's just
you want it like
a
that?
different time.
No? Okay.
That's
What
it.
I
That's
have
it.
is correct.
Okay.
That's it. That's
I was gonna
it.
ask.
You know, more work on my side because I have to
10
go, oh,
hours.
he did it this way.
Yeah.
Unless somebody else has done it that way before.
But then the moped down work.
I was gonna ask, like, if it's not in kilograms, how would we put it in any other way?
If you're not using the standard units, then you just have to keep track of it.
Okay.
So, mass of sun.
Mass of the sun.
And
We
it
did
just
not
goes to
cover-
something else that was
We
being talked about.
found the mass of the sun.
So I know that I have two formulas for the force due to gravity. I got big G, mass 1, mass 2 over r squared, and I also
Hey, I
have
remember
big G.
Yeah.
So I can find G simple enough because this is usually the smaller mass, but this is the mass of something. That's going to cancel out with one of those, so this would be G times the mass of whatever the central object is. I'll just put C for central object over r squared is equal to G.
And just to make, big G is the 6.7 number, right?
Yeah. The gravitational constant,
Is it 10 to the negative 11th or the negative 7th? I can't remember.
negative 11.
And
Wait.
It'll be written on the first page of the
So is
test.
that like that? Is that like a given constant for all the problems where big G is, or is it just?
G, big G is a constant that we are considering universal at the moment.
and the little g is the acceleration due to gravity.
Yes.
Okay.
So
Oh.
where did the can you explain kind of
That's
what the constant represents?
Gravitational acceleration.
Like,
What the constant represents is, Cavendish was first doing his experiments. He recognized that the force due to gravity was dependent upon Cavendish actually found the value. I guess Newton and Cavendish will throw them together. They realized that the force due to gravity is related to both masses and divided by r squared. So the bigger the distance, the smaller the force of gravity, by r squared, and then the product of the masses tells you the force due to gravity.
And the masses being the big thing and the smaller thing.
Whatever, actually, this formula works for any two masses.
Okay.
Works for you and the book in front of you.
Me and book. Okay.
Any two masses. So this right here is basically a unit thing. Because this needs to be in newtons, this is kilograms, and sorry, if we're in an SI system, this would be newtons, that'd be kilograms, and meters squared.
Oh.
So in order to get it into the right unit system, there has to be some factor here.
Okay.
So that's basically what it is to get it into a unit system that is easier to work with.
Okay.
Okay. Okay, kind of makes sense.
Okay.
I was just curious, like, what that is for.
I was about to ask the same thing too.
Yeah. In the CGS system, this would be grams, centimeters squared, and then that's going to be
Centimeters squared.
off by a factor of, I think, 100. So it'd be 6.67 times 10 to the negative 13th or negative 9th.
I don't know, it's a small amount.
It's 9 probably. All the other ones are to the 9.
It would be something.
How do they even find those numbers? Oh, do they just do experiments to figure out what G is? Like,
Oh,
how
what
they-
this value is?
Yeah.
Yeah, this is this is what I consider one of the most tedious experiments of all time.
Really?
You got two masses. Set. So you basically got this thing with two masses sitting on it. From above, you have a dangling mass. So that's attempted at a 3D drawing there. So you got the mass that's basically set right here, and then you put another set of masses right there.
Okay.
This set of masses here is going to turn
What?
because it's attracted. The masses are attracted to each other. So
Yeah.
the mass is going to get attracted to it, and it's going to, basically the wire that it's hanging on is going to twist.
Because of the
Because these two masses are attracted to those two masses.
Okay, and then they just do the math to figure out what that.
And so, because if you know the material and you know the specs for it, then you know how much torque is required in order to twist it. From that, you can figure out the force that's actually being applied.
Okay, and I can do that over and over. And data gets compiled, and it becomes like an average.
Yeah, or something like that.
Something like that, yeah.
And you just hope that nobody sneezes while you're doing the experiment or opens the door or. Now, it was done in a glass enclosure, so, but still, today if you did it, if a truck rumbled by, then that would mess it up too.
Dang, that is a
I'm curious, like, since it's based on R, which is like the distance between them, does it get faster? Like, it's very minute, but does it get faster the more it turns?
Except for the fact that this wire gets harder to turn the more it turns.
Oh.
And so this will start increasing in basically resistance. Not the technical term for it, but it'll resist the twisting, and so it will come to a standstill.
Yeah.
How did they? So you said Newton did that?
Cavendish. Cavendish is the one who did the experiment. Newton's the one who figured that relationship out, the product of the masses and the distance.
Oh, and Cavendish just found the constant. He just found G.
Yeah.
That's pretty cool, because one of them is like a theoretical physicist, and the other one was like experiments and stuff. Yeah, that's pretty cool. One of them would actually like experiment to figure it out, and the other one liked to.
Yeah, I think there was like 100 years separate. They didn't live at the same time. It's not like Newton said, "Hey, try this theory out."
No.
Newton wrote it down, and eventually someone picked it up and said, "Hey, this might make an interesting experiment."
But in like the grand scheme of things, they were kind of neighbors. 100 years apart, not that long.
So,
It's a long time, man.
It's
all right. I think we're talking about gravitation. That's right.
We just figure out everything.
Sorry, I was curious where that came from.
Sorry. Alright.
So we have a formula for the acceleration due to gravity. If you plug in the radius of the Earth and mass of the Earth, you should get somewhere around 9.8 meters per second squared.
Okay. So
What is that beside the little m?
I put a CO there for a central object.
R is the distance of the object, or what?
Center of gravity to center of gravity. So basically center
Okay.
of Earth to center of mass of whatever you're.
So if we were trying to find G for the Earth, it'd be between the Earth and the Sun.
Center of the Earth to center of the Sun.
Okay. So that, okay.
Which is probably not a whole lot different from surface to surface in that case, but.
So Mars has a farther distance, so it would have less gravity?
And it has a smaller mass too, so yeah, there's less gravitational pull on Mars than there is on Earth.
Okay.
Venus is about the same size as Earth. I think it's a little bit smaller, but it's closer, so, you know, more. I suspect that there's a greater gravitational pull, but I don't know for sure. So you've got the mass and R are both dropping, but I think R has a much more dominant effect. So I suspect Venus will have a greater gravitational pull.
Okay. Sorry if I ask a lot of questions like that, but it just helps me figure out the relationships.
Okay, no problem.
How do you calculate or confirm your calculations of the force of gravity on other planets? The force due to gravity, the acceleration of the force due to gravity.
You mean little g on other planets?
Yeah, like I assume that this equation is used for that, but how did they confirm that?
You can, all right, so I can look this, I can get Mars and I can come up with an estimate for the size of it. So I can figure out the radius, just staying here, I don't have to actually go there. The mass of it, if I assume that the composition of Mars is similar enough to Earth, that the densities are about the same, then if I know the size of Mars versus the size of Earth, I can come up with an estimate for the mass of Mars. If I know the mass of Mars, I can then come up with an estimate for the value of G.
Okay, that makes sense.
And then I can take a satellite and ram a satellite into it and look at its acceleration as it falls. Also, I can find, this is the mass of the central object. I can also look at the moons going around Mars to come up with the mass of Mars. Probably more accurate than assuming the same density as Earth.
Would big G be the same?
Big G should still be the same.
And in one of the videos you said that was big G is technically only confirmed for our solar system?
Yeah.
Oh, so because we can only measure it so far, but there is a chance that we got far enough from where we are that constant might be different.
The possibles in terms of constant, it might be the same throughout the entire universe, or it might not be. The way things are behaving is not what we expect. So there's various theories that have come about why they're not behaving the way we expect.
Yeah.
One of them is the idea of dark energy or dark matter. Two different things. And another idea that I think is sort of passé at this point is that the value of G is not the same everywhere. And there's also another place where you might go, is it really constant? The value of G, let's say that it is constant everywhere in the universe right now.
Right.
That doesn't mean it's the same value that it was 3 billion years ago.
Oh.
So it might change with time, just not change in space or distance.
Like, yeah, because the universe is ever expanding. So it could change.
It's possible.
Right. We're just not gonna know yet.
What is dark matter?
Don't.
Dark.
I'm so curious.
One of the explanations for why the universe is not behaving the way we expected, that things are moving faster than we would think, is that there's additional mass there that we can't see. That's the term dark, we can't see it.
Oh, okay.
Now, there is evidence for it. There's this thing called gravitational lensing, which has been noticed that if I have this something large object like our sun, and then we're here on Earth, and our moon just happens to be in the right place at the right distance, so that if you've ever seen a solar eclipse, you'll know what I'm talking about, where the moon, basically from our point of view, basically covers up the main disk of the sun.
Yeah.
If you haven't seen a total solar eclipse, the next opportunity you get, it is worth it. It is absolutely amazing. The one that was, I guess you can see it in South Carolina a couple years ago. So if we blocked out the sun, we can now see things on the other side that we couldn't see before. If I have an object, say right there, let's say there's a star, a distant star, that light is coming at us, and based upon Newton's theories, that this mass here will cause the light to bend. And if that's the case, it will look to us like this object is here and here, but it's actually only one location.
Wow.
Matter of fact, if it's perfectly lined up, you would actually see this smear of light.
Also, you see two objects?
or more.
or more, but it's one thing.
From
Yes.
one,
It's just being
One
bent by the sun being in there.
and that's what the idea of dark matter is.
So there are pictures that NASA has taken from, I guess, Hubble or one of those telescopes, where you actually see this, there's this dark area here, you can't see anything in it, but you see the smear of light along the edge. Because, which would fit with the hypothesis that there's some huge mass here causing light to bend, and you get this gravitational lensing.
I think I saw that. Wasn't it pretty recently?
Mhm.
With that new Webb telescope or something that they put up there?
Oh, it's possible that they have even better pictures
Yeah.
now. I don't think it was the Webb telescope when I saw, but
Okay,
it
yeah.
compared,
I saw it recently. It was really, really cool.
some of the pictures from the Webb telescope are just absolutely phenomenal.
Yeah.
I had read an article about when it was about the whole thing, the whole topic, but came up when that thing with NASA happened, when they had the pictures. Apparently they've been like theorizing that dark matter or something. That's what they're calling it. I didn't really get a lot of specifics about it, but they've been thinking that there's something, and they just couldn't prove it for the longest until that happened.
Yeah, so,
And the idea was that you can't touch it, you can't see it. You could they just know, they now have proof that it's there, but you couldn't physically see it or touch it if you wanted to. It was crazy. It was a weird article.
it all depends on what it actually is. This is the point where the theorists step in and they make up stuff. And in 200 years from now, it'll turn out that most of them were wrong, but there's gonna be some guy who's right.
One guy.
Many's praised.
Yeah, he's brilliant, he's a genius.
What a genius, we're gonna name this after him.
When all he did was just cook spaghetti and throw it against the wall and come up with stuff. I had
That is a good
a
one.
friend in grad school who was working on his PhD in astrophysics, and I went back to work full time, and then I came back to grad school. When I came back, he said, "Yeah, I was working on this. I'm working on something different right now, but when I first started it, I didn't realize that 99% chance it was pure crap. 1% chance it was actually incredible, potentially Nobel Prize winning stuff." It was not Nobel Prize winning stuff.
Ah.
All right, back to this. I'm not quite, the gravitation formulas are problems